Well, first of all, thank you so much for that wonderful introduction, Dylan, Georgina, Paul, Luke, Tien. It's very, very nice to meet you. Anyone else who's also on the call, whose name I'm currently, Dushan, thank you. Whose name I currently can't see. It's very, very nice to meet you. Just a quick introduction. I am a CPO and technical product manager. I've been an AI and machine learning enthusiast way before it was cool. I've been playing with neural networks and the old natural language toolkit based on Java since approximately 2008, even before TensorFlow was really a thing. And throughout my work, I get to apply this passion, focusing on delivering artificial intelligence and machine learning driven value propositions almost exclusively. The good news is that and by the way, you can see the slide that I have on at the moment. Yeah, perfect, fantastic, because I can't see it because I'm sharing apparently, so that's good. But what that leads to is that requires me to my job essentially requires me to be completely self-indulgent and very closely follow the AI and ML developments in the space, and that makes it really easy for me to present on the latest developments and the latest research in AI, which is what we're going to do today. Now, before we're going to get started with sort of like a new community like this, it's a little difficult to gauge the right balance of technical granularity. And so what I'm going to do throughout this talk is I'm going to keep this particular session to a discussion that exists sort of at not at a 10,000 feet level, but more at a healthy 1,000 feet conversation. So less math, less code, more focusing on a principled discussion. And now what does that mean for you? If you are an AI researcher yourself, or you're working in the AI and machine learning space, there is a chance that you might recognize or that you might have heard about some of the things that I'm going to tell you about today. But you might not have heard about them in the exact sequence that I'm going to present them to you, which could still be valuable because it tells a cohesive story. But you're probably aware about sort of the general developments in the space because obviously that's your job, right? If you are not an AI researcher, what I hope to do is to take what I believe are the three most prevalent paradigm shifts that we are seeing in the AI space, particularly this year, and sort of illustrate those with the most recent papers that have come out sort of in the last 2 to 3 weeks. So it's all very fresh. The space is a very fast-moving space, of course. And what I'm going to do is I'm going to overlay sort of a story around this that lets us sort of product people get sort of a feel where all of this is going and where the major thrust in the AI space is currently and where it's headed. Now, the way I will break this up is I'll talk about three major paradigm shifts that have occurred in the AI space and things we have seen significant traction on over the last couple of weeks. I will then talk a little bit about new capabilities that exist in a productized format that underpin these developments. And then at the end, I'll introduce and talk a little bit about a massive issue or outstanding problems that are sort of still sitting at the end of this wonderful rainbow. And those need to be solved. We need to have additional research on those yet because we don't yet have great solutions for those particular problems, if that makes sense. Right. So from that framework that I just presented, you can probably tell that what I'm not going to do is to include essentially every piece of artificial intelligence news out there. The space is moving incredibly fast, right? Part of that space is a little bit scary, and some of them might even be paradigm shifting, but they aren't likely going to dictate how the rest of the year will essentially play out. And that's all I can say for the rest of the year because, who knows what's going to happen next year. So just to give you an example, right, of things that are happening, but that aren't part of those major trends, are these two articles that came out in the last 2 weeks. Right? You might have seen this news about brain in a jar biocomputing. We call them wet components, where they were essentially in China, a couple of researchers were essentially able to control a robot by using more efficient, energy efficient organoids. which is really scary on the one hand, right? But on the other hand, it's also a little bit of entertainment because it is somewhat of a standalone effort that is not currently defining where the most of the research goes into. Something else that's probably worthwhile mentioning as a side note are MLP, so multi-layer perceptron alternatives, right? Like the Kolmogorov-Arnold networks that a lot of people have sort of dubbed a promising alternative, leading us to ultimately machine learning 2.0. Spoiler alert, doesn't turn out to be that way. But these are all efforts that are interesting and might become relevant sort of next year, but currently a little bit standalone. And so what we're going to focus on instead are trends and developments in the space that show promise because they mutually reinforce each other and therefore build momentum that indicates sort of like a persistent progress in one specific direction and the way products and businesses are going to be developed around, right? And as I mentioned, I'm going to focus on the last 2 to 3 weeks. So the one we're going to start with is a quite massive sea change, and that is Meta's move to open source Llama 3.1, which is currently the only open source model that can compete and in parts outperform GPT-4. And essentially, why does this matter? You can see here the results here compared. So to some other areas, there are certain tasks that Llama 3.1, the 405 billion model, which is the largest, outperforms Claude and GPT-4 in various areas, right? Now, why does this matter? It matters because Meta just made intelligence free for everyone, right? We need to understand that AI is a general purpose technology, and Meta realized that intelligence is a thing that customers essentially won't care about where it comes from. Similar to how all of us don't essentially care about where our electricity comes from, we have the same dynamic happening with intelligence at the moment, right? There's different products out there. In essence, what you care about are the products that are built on top of those LLMs are capable to solve a particular problem. You don't necessarily care about which underlying model they end up using, right? And by open sourcing Llama 3.1, what Meta essentially did is that everyone on this call and in the world can essentially download the model, deploy it themselves, build products on it, and compete with everyone else on this, right? And that means more competition. That means that prices will go down. It means that margins in the product space will shrink. But ultimately, it's great news for us consumers because we'll have more experience available to us, and also for us product managers, because that means we have more optionality in the way we're building and architecting our solutions. Now, why would Meta go ahead and spend roughly $500 million to do this? You think that they do this to, go with a standard modus operandi, which is to collect everyone's data, but that is not possible. Because Llama, as a large language model, has no capacity to phone home. And what that means is that any data that goes in or out is completely out of Meta's control, right? The reason why Meta does this is because they want to essentially leverage 3 major benefits, or 4 major benefits, I should say, right? On the one hand, Llama is sort of like rapidly becoming a standard in the industry now because it's the most accessible. On the other hand, that means that there are a ton of people who are going to do research on this, right? Which is work that Meta gets for free. And the third element here is that there is a strategy which as product managers call commoditize your complement, which means that Meta doesn't currently have an existing business model as part of their portfolio that takes money from charging for AI services, right? That's not what they do, right? What they do is they sell ads. But who makes money from charging for AI services? That is Microsoft and Google. So obviously Meta did this in order to cut their competition somewhat off at the ankle, right? There's also a fourth strategy in play here, and this has to do with the second paradigm shift that I'm going to introduce here. And that has something to do with the role that LLMs play in the overall architecture of AI and machine learning driven value propositions that customers are consuming. So about 2 weeks ago, Andrej Karpathy, one of the co-founders of OpenAI, shared his vision for the future of computing, right? You have the sources down here. I'll share those slides with you after the talk. It's a fantastic talk that he gave at UC Berkeley. I would highly recommend you watch it. But essentially what he says is he believes that we all feel, and folks in the economist space agree, is that the AI boom is a little bit reminiscent of the dot-com boom. And Mr. Kapathy, so Andre, believes that this is because the nature of computing is fundamentally changing. And in his talk, he shares this idea that we're entering into a new computing paradigm, right? Where instead of having a central processing unit, so a CPU, that essentially works on instructions over bytes, we have large language models that are kind of like the central processing unit, but it works on tokens instead, which are essentially vectorized string pieces, right? And in addition, you also have this context window of tokens with an LLM instead of the random access memory of bytes, which you have in a computer. And they also have other components like disk and everything else that they interact with. So it's a bit like a computer, and you might say there are a lot of similarities and a lot of parallels that can be drawn here. Now, for everyone on this call, you might say that, well, LLMs are still running on a CPU. And for now, yes, that is true. But keep in mind, there are two major developments that might be worthwhile talking about. The first development is we all keep hearing about OpenAI entering talks with chip manufacturers. Over the last 2 weeks, we've seen them entering into talks with Broadcom and other chip manufacturers to develop what they term their AI superchip. That's exactly what they're talking about. They're talking about creating their own chip. And yes, while chip scarcity tends to be a factor in those strategic decisions, the proposed architecture that they're also currently floating around is optimized for processing vectorized string pieces rather than numeric I/O input and output, if that makes sense. Right. The second dynamic that is worthwhile mentioning here is that by looking at the LLM in this way, you are essentially positioning it in the role of an orchestrator of workloads rather than seeing it as a workload itself. And that is a significant paradigm shift because it leads us to this third thrust that we're currently seeing in play out in the industry. And that is a macro conversation that we've seen evolve over the last 3 to 6 months or so. And that is the move towards the agentization of LLMs. Right. And it's essentially the recognition to say that, well, whatever user experience AI wishes to bring to bear, right, it essentially requires the underlying architecture to do a ton of problem solving. Whoops, I'm jumping ahead here, right? And the best way to do this tremendous amount of problem solving is turns out to be not a single digital entity that solves all the problems. It just turns out that it is much more efficient to train many different digital entities, specialize each one of them on the problem they are specifically trying to solve, and then have them collaborate and work with each other in the background before serving the response through one singular interface, right? So what this may look like is that if you are talking to Siri or Alexa or GPT-4's voice interface, right, you might talk to it, it might respond to you in the same voice, but in the background, there are lots of agents that are working with each other to solve a specific part of the task that you gave them, right? And this is where this orchestrator idea comes in, right? Where essentially where we're saying, okay, we're building specialized agents, right, that can focus their role in a way that makes them the best at solving a particular set of problems, right? You can send those agents to the right school that is just focusing on that one particular problem. As a consequence, you can make the individual agent much smaller. That means it is less expensive to train. And you can also make them more performant, meaning they could also be so small that they could even run on your own device, meaning they do not need to have connectivity on the cloud, and then hopefully in the future, maybe even on your phone or other mobile devices. And of course, similar to how serverless functions work, right? If you do not require an agent for a particular period of time, right? Because that specific problem doesn't require any attention, you can just spin them down, save yourself the compute, and spin them back up when it comes time to rely on them, right? Now you might say, okay, these paradigm shifts are all really interesting, but Mike, how do you know that we are working our way to really towards those? And this is where we're going to go into a couple of papers now, because there's a ton of research that is directly supporting these paradigm shifts. And keep in mind, while these trends have been observed, these larger paradigm shifts have been ideas that have been circulating in the space over the last couple of months. The following papers that I'm going to show you are only 2 or 3 weeks old, so that's very fresh, right? So the first one that I wanted to show you here is a paper about XLM1B. It's also called Einstein Tiny Giant. It's a small LLM that was, again, open sourced by Salesforce earlier this month. And essentially, what you have here is I included the paper for you to look at. You can even go on GitHub, download the model, and play around with it yourself, which is really cool. But essentially, it is a 1 billion parameter model that was specifically created for performing function calling. And what that essentially is that you give that particular model a particular prompt, and that model then figures out which functions are the best to call. So which APIs to reach out to in order to complete the task, right? Which is a really, really interesting problem. And obviously, also aligns with the idea of agentized AI, as we've just talked about, right? It's significant because in order for agentic AI to be real, right, especially on devices, the AI needs to be really performant in terms of whenever they need to decide which functions and/or API endpoints it ought to call in order to talk, obviously, with other agents, right? Again, the LLM is sort of taking on the role of an orchestrator, right? But deciding which other orchestrators it's going to be in communication with in order to solve the user's problem is in itself a problem that we are developing machine learning models for. This particular one was developed in order to solve those problems, very performant in a reasonably resource scarce environment, but performs at models that are sort of like 7 times its size, if that makes sense, right? Another paper worth mentioning that is sort of underscoring the idea of agentic AI and the orchestrator model is Route LLM. Also only a piece of research that is about 2 weeks old. And what Route LLM is, it's essentially an open source framework for cost-effective, jumping ahead here, for cost-effective LLM routing, right? And what that means is there is a whole paper, that dives into this, and you again have the open source code that is available for you here. But what that means is that to improve performance, right, you try to have an open sourced routing system or an open sourced framework that can help you with assigning different LLM systems, different agent roles or different tasks in order to create this distributed system of compute and have each LLM talk to and work with each other in order to solve particular challenges, right? So one use case, the way you can imagine this is that one LLM, if you were to give, Route LLM a particular prompt, right? You'd say, I would like to create a travel schedule or something like that. Route LLM will go ahead and appoint one, let's say Llama, 3, to generate the initial output of that travel calendar. It then appoints another one to judge that output. The third one then converts that into instructions, and the last one then goes and executes the bookings, that kind of thing. And that is significant because whenever you create value in any product scenario, right, cost tends to be an independent variable of that value that's being created, right? And what we've seen is specifically in code generation use cases, so when AIs need to go and create snippets of code, you can essentially take GPT-3, which is significantly cheaper than GPT-4, split it into teams of agents, right? So you have one that might be focusing on analyzing the prompt, the other one generates the code, the third one tests it, and the fourth one supervises the whole process. And you end up getting something that is comparable in terms of output and effectiveness with GPT-4, but at a fraction of the price, right? And so we have this trade-off in the industry right now, which is this consistent question when we're building solutions where we're saying, well, do we use the best and the brightest and the most expensive LLMs, or do we take an agentized approach where we train by task and become more cost and performance efficient, right? One of the first iterations of where this was proven successfully was by NVIDIA using Minecraft, actually. So you may have heard of a project called Voyager last year, which was a project by NVIDIA where they created a collection of agents that work together to play Minecraft. To play Minecraft. And what we had here is the system created code to represent a set of skills. Code creation is currently most powerful in GPT-4, so that's what they used it for. And then they passed that on to GPT-3 in order to create a description that then created a skills library. And then when it came to selecting the right skill in order to interact with the world, they also relied on GPT-4 in order to select the right skill, because it was cheaper and is more of a manual task and is more performant for the task at hand. So that's how NVIDIA approached their particular let AI play Minecraft problem. Also, as you can see, an agentic approach, if that makes sense, right? And the way this route LLM works is that you input a query, right, and then it decides which LLM to route the query to. And the LLM that tends to be best suited to execute that task for you is going to be selected. And essentially the way they do this, they base this on a binary classification algorithm using human preference labels from Chatbot Arena. Quick question, does anyone on this call not know what human chatbot what Chatbot Arena is? Have you seen this before? No? Yeah, some have. Good. Andre has. Well, no. All right. I'll just quickly show you. Right. So essentially, what this is it's a little tool. I'm not sure whether you can currently see it. Let me just show you here. Yeah, perfect. So it essentially takes two machine learning models and puts them against each other, and I'll enter a prompt and say, tell the audience, right, of the living library that they are beautiful, right? And then it creates those two different outputs, and you can choose which one you like best, right? This one seems to be a bit highfalutin, so I'm going to go with B. And essentially, what we are seeing happening with Route LLM is, I'm going to stop sharing here again. So let's see where the screen comes in. You can see the paper too. Is that correct? Yeah, wonderful. So essentially, Route LLM just goes and takes that data from the chatbot and says, well, one of those LLMs for a particular task is weak, one of them is strong, right? So we're just going to route you to the strong one. That's how the classification algorithm works. In essence, it's a little bit of cheating, right? It's not very complex in the background, which makes that solution even more compelling, but it's interesting that it definitely exists, I would say. And again, underscores that larger trend, specifically relating to using AI agents for the right job, right? Now, I've just shown you through two developments that are underscoring those three paradigms that I've shown you. I also promised you that I would round this out with a few problems that we still require additional research on, right? And this is, and this is where we are approaching the third and the fourth paper, which is there are still a couple of problems that do exist when we have large language models work with each other, right? And that is on the one hand, they tend to invent their own language. You all would probably remember that viral news back in 2017 when Facebook pegged two AIs against each other. The news falsely reported that they had to emergency shut them down, which was never the case. But essentially, those two AIs started inventing their own language so that the developers and the engineers couldn't tell how they were communicating with each other. And the media picked up on it because it was incredibly creepy. Now, the thing is that it is not as a massive problem that AI is taking over the world. That's not the case, but it makes debugging and analysis really a lot harder, and we still don't have a good way of addressing this particular problem, right? Attempts have been made to address this via a thing called representation engineering. Essentially, representation engineering is a portfolio of techniques that we borrowed from actual neuroscience, right? Where you're trying to analyze the neural network, right? But instead of looking at an individual neuron, you say, okay, this collection of neurons that represents, you know, the concept of a plane or the concept of a watch, and you have like these regions in the neural network that you can identify. But that hasn't quite helped in terms of solving this particular problem. It has been shown to be inefficient up to this point, right? The second problem that we tend to face in this area is it's also a rare problem, but it's not so rare that it can be entirely ignored, and that is the phenomenon where two LLMs accidentally jailbreak each other. So LLMs usually come with constraints, right? If you're ChatGPT, you wouldn't want your LLM to tell someone the exact steps of creating a chemical bomb, things like that, right? Or create output that might be somewhat offensive to people, or leak people's individual data, right? Or personal data. So therefore, these LLMs are essentially put into constraints, but there are always ways to jailbreak them so that you can remove these constraints. Now, again, there's not a lot of research on it because research funding in AI safety has tanked in the last couple of months. But in essence, the way this works is if you have two LLMs that are talking to each other over a period of time, with enough time through random permutation, they will end up jailbreaking each other without being told to do so first. And while this isn't a probable outcome by any means, if you look at the order of magnitude of operations that we're looking at when we're talking about agents talking with each other 24/7 round the clock, even a rare occurrence with a low probability is statistically inevitable, right? And that means that as a business, if you're building solutions in an agentized setting, you're going to run into problems. These can be performance problems, they can be unreliability problems, but they can also be safety problems, right? Leaking people's credit card information or leaking people's addresses, or even worse, doing concrete damage, right? It might, do smaller things like unsubscribe you from Netflix, which is not great, but, leaking your social security number and personal details, that wouldn't be awesome, right? Now, the solution to both of those problems is currently the best solution that we're sort of kind of looking at is where we're saying, okay, we're trying to explore what is called the latent space. So you have generally with neural networks, you have an input layer, you have an output layer, and the layers in between, they're called the latent space. But that is a really, really hard thing to do. What I've included a paper. It's a fascinating read. It's actually also really, it's an easy read as well. Essentially, what they're doing there is they're trying to deconstruct the neural network to divide the neural net into components that can be naturally understood. Unfortunately, what you have with neural networks is the most natural computational unit of the neural network. So the neuron itself turns out to be naturally unfit for human understanding. And this is because neurons are what we call polysemantic, which means they respond to a mixture of seemingly unrelated inputs. And I can show you what that means here. So this is a neuron that was being analyzed as part of this paper that I shared with you here. And you can see that this particular neuron takes a mixture of inputs to make decisions, and that is a mixture of academic citations, some dialogue, right? A few, let's see whether we can find it, right? A few HTTP requests, right? Some HTML, but also a whole bunch of Korean text, right? So for us humans, we don't know how this came to be, right? And we can't necessarily make heads or tails with it, but that's why they say that neural networks are somewhat of a black box, because the neurons themselves are essentially unfit for human understanding. But what this particular research paper is trying to do, right, and I'll show you here what that looks like here in a second. What that tries to do is they're essentially trying to apply another learning methodology that's called sparse autoencoding to extract the interpretable features from those neurons. The only unfortunate thing here really is that it is not scalable whatsoever. So what they did is they essentially took a one-layer transformer with 512 neurons. So essentially what you can imagine is that this layer and this layer doesn't exist. It's just one layer here, right? And they were barely able to introspect the associations that each of those neurons uses in order to make their decisions with, right? So there is still a bunch of research that needs to be done in this area. We've just started on this. It is a massive problem that everyone is still trying to solve, right? But we aren't quite there yet, if that makes sense. Now, but even if this was scalable, there's also some interesting research that came out, I think, just a week and a half ago. And that is that we currently have no solution for a thing called recursive model collapse. And essentially what you have here is a research project where researchers looked at AI models, right? And they looked at what happens if you train AI models on synthetically generated data. And what they found is that those models tend to collapse. Which is going to be interesting because, as I mentioned, right, 3 weeks ago, Llama 3.1 just open sourced their own large language model. They famously came out and said that they trained on generations of synthetically created data. And just this week, we have seen signs of model collapse occurring in that model. And people are already investigating it. Researchers are already investigating it, whether 3.1 can actually be used long term or whether that's a problem. And what model collapse is essentially it's a degenerative process that affects generations of learned generative models in which the data they generate ends up polluting the training set of the next generation. So the way you can imagine this is if you go to one of the AI image generators, right? If you were to generate an image and then you take that image and use that to train another AI image generator, and you do this over and over again. And the problem with that is that LLMs or artificial intelligence or machine learning networks aren't perfect, right? And even if it's imperceivable to the human eye, every time they generate an output, they contain artifacts, which are small, tiny errors and noise that then propagate through the learning process, and they tend to become more and more pronounced, and that leads to the eventual collapse of a model, right? So the paper here that I'm going to show you here is this paper, right? You can read through that in your own time, but it's really, really fascinating. So what you see here is a measure called perplexity. Similar to humans, the more perplexed you are, the worse you get, right? And down here, you see the number of generations of training that they applied. So essentially what they said here is that later generations start producing samples that would never be produced by the original model. That is, they start misperceiving reality based on errors introduced by their ancestors, right? And we find that models trained on generated data are able to learn some of the original tasks, but with errors as seen from the increased perplexity. And the way you can interpret this chart is it's additive, it's cumulative. So with each generation, you have this amount of error and noise being introduced. And while this tapers off a little bit, in order to make synthetic data a reality, this chart would have to go into the negative. But with every generation, it introduces errors, which ultimately then leads to the model falling apart over time. And that is obviously a huge problem because while synthetic data would be a huge unlock for AI companies, right? This study shows that this is ultimately unsustainable over the long term. Yes, AI companies had the luxury of taking very original content from the internet because essentially everything was human generated, right? They were able to do this because that existed before at the time AI existed. But now with the oversupply of images, text, API, technical documentation, all that sort of stuff, that time is gone, right? And what we are hopefully not going to see is AI entering into this death spiral where the oversupply becomes so huge with the lacking capacity to not being able to differentiate between a human-generated piece and an AI-generated piece, right? They're all poisoning their own well, but that research seems to point towards that, so that's definitely a space to watch. Cool. All right. So that, in essence, sort of rounds out my presentation. Now, I would be amiss if I wasn't going to mention this. This is a little attempt at solving that particular problem. A friend of mine asked me to mention this, which is essentially a solution that I'm involved in where we're trying to build a proof of provenance system that is essentially intending to solve the issue for both creators and AI companies to address the artificially generated oversupply in the space. So what we're building is a platform where essentially you can go ahead and fingerprint your original work, right? AI can then go and scrape it against a fee that goes directly to the creator. And in exchange for that, artificial intelligence companies get really compliant licensed training data that they can also use for attribution for their original content creators. So very shameless plug here at the end, but ultimately, if you want to learn more, right, you can go to Blinks AI and sign up for our beta. We're hoping to be live here within the next month or so. But overall, right, summary, just before I'm taking questions, right, 3 major paradigms. Intelligence being free now, it's going to increase competition, reduce margins, right? Has large-scale LLMs much more accessible. We're expecting other LLM companies to follow in terms of open sourcing their own models. We have a paradigm shift that goes somewhat along with that, where the LLM is slowly becoming the operating system that takes the role of an orchestrator, right? And that also is supported by our move towards agentized AI or agentic AI, where we are seeing different LLMs being deliberately employed to be trained on and solve very specific narrow tasks, which improves the performance, the reliability, and the cost of those models. Included a couple of papers here for you to look into. And that concludes my talk. Sweet. So that was a lot.
Great stuff, mate. Really, really interesting. And
excellent.
I'm sure there's going to be quite a few questions from people. Does anyone want to jump in then?